My name is Robert Denise. I was the tactical mission manager for the surface phase of the Phoenix mission. In talking to a large crowd, it's always a challenge in that I inevitably have people, the PhDs walking out the door saying, he talked to us like we were 12-year-olds. Of course, we have 12-year-olds here who are going to be walking out the door saying, man, he thinks I'm a PhD. So I'm inevitably going to be missing the mark with everybody at least once tonight. My hope is that everybody walks out of here with a few interesting things that they learned about Mars, about the Phoenix mission, about JPL in general, and that we all come out of the whole thing a little better off. What you're looking at here is an artist's conception of what it looks like at the Phoenix landing site right now. Well, of course, you have to remember that the Phoenix lander landed at north of the Arctic Circle on Mars. Mars has a tilt on its axis. Its axis of rotation is tilted similar to Earth, which means that north of the Arctic Circle, during the winter months, it's dark. It's dark and it's cold. And we're expecting right now the Phoenix lander is completely encased in CO2 frost to a thickness of about 30 centimeters. The batteries are long since depleted. Nothing is operational, and it's dark. It didn't always look that way. Earlier in the mission, we looked a little more like this. This is also an artist's rendition, but that's okay. Just to give you a little sense of scale, a little sense of what we sent, the solar arrays here on the ends are approximately 2 meters in diameter, 2 meters here, and the center, the deck is just a little more than 2 meters, so it's a little more than 6 meters long, on order 20 feet or so, just to give you a sense of scale. This mast here is 1 meter tall. This one here is just short of 1 meter. And incidentally, the landscape there, interesting though it looks, is far more hilly than where we actually landed. That's okay. The artist wanted to have some fun. Why did we go? We went because of data like this. Now, this is what you're looking at here is a composite image of MRO data, Mars Reconnaissance Orbiter data, taken with the gamma ray spectrometer instrument. The GRS looks at Mars in the gamma rays and sees using, well, just to be really technical, it's sensing epithermal neutrons, which are moderated by the presence of hydrogen. In other words, where there's hydrogen, that is, they get less neutron signature, and that's the blue area near the pole, which means that we see an abundance of hydrogen near the pole. And remember that neutrons are fairly robust little buggers and that they will penetrate close to 1 meter of rock, which means that we know there's hydrogen somewhere in the top meter of the subsurface materials near the pole of Mars. Now, the popular theory was that hydrogen was chemically locked in a substance called hydrogen hydroxide. Chemical signature HOH. Some people use the shorthand notation H2O. Some people call it water. Okay, most people call it water. So we think that there's a bunch of water in the subsurface material near the pole of Mars, but only by virtue of being able to see the hydrogen. And so the Phoenix mission was designed, was proposed in 2003 by Peter Smith, a professor at the University of Arizona, to go to the pole of Mars and to dig down in the subsurface material and verify that the material, the hydrogen that we were seeing, was representative of water. Why water? Why is water important? NASA has long had a program concerning Mars saying, follow the water. Water is important because water is a very strange chemical. It has, well, 3 real oddball properties. Number one, water has a liquid phase that spans a wide range of temperatures, wider than a lot of substances. Water chemically, the molecules are polar. That is, one side of a water molecule has a greater electronegativity than the other side, which is why water can be used as a solvent for both acids and bases, which makes all of the acid-base chemistry work, which makes all of organic chemistry work. Water also has one other really strange property, in that when it transitions from the liquid phase to the solid phase, it increases in size, which means that ice floats in a glass of water. Now, most people say, of course, ice floats in a glass of water. Everybody knows ice floats in a glass of water. But realize that water is unique among the substances that you are exposed to on a daily basis that actually does that. Most substances, when they transition from liquid phase to the solid phase sinks. Now imagine for a moment how the world would be different if ice sank in water. It would mean you're holding a glass of water and the ice cube would be sitting at the bottom. But it would also mean that the oceans of the world wouldn't be liquid oceans with ice floating on top. They would be solid ice at the bottom with a layer of water on top. Weather, climate, if it existed at all on Earth, would be vastly different. Life, if it existed at all on Earth, would be vastly different. This property of water to expand when it goes to the solid phase is unique and very special and very integrally linked with the development of life on Earth. And so water is important. Now, because we look at Earth, everywhere we look, we see life, we see water. We see water, we see life. The two go hand in hand. The question is, does the presence of water mean the development of life as a general rule? Well, Earth is a single data point. We'd like to get another one. Actually, we do have 2 data points. We have visited the moon enough times to know that there's no water and there's no life, though that doesn't really confirm or deny the supposition. Mars is the next closest target that we might look at to look for the correlation between the presence of water and the development of life. From Earth orbit, from Earth-based satellites, from Mars orbit, we've seen a lot of evidence of the existence of water in the distant past of Mars. Schiaparelli saw the canale on Mars back in 1870-something, long ago. The Mars orbiters, the Mars Reconnaissance Orbiter, Odyssey, Mars Global Surveyor, they've been sending back marvelous pictures of Valles Marineris, this canyon system that is 3,000 miles long and that is clearly cut by water. We go down to the surface with the Mars exploration rovers, with the Pathfinder lander, and we look around and we see a lot of evidence that water was existent on Mars in the distant past based on the chemistry, the geology, the rocks. We see layered terrain, we see ripples in the layers in the rocks. We say water flowed over this and they haven't found any water. But we saw that hydrogen near the pole, and so in 2003, like I said, in response to a Scout mission proposal, Peter Smith from the University of Arizona proposed the Phoenix mission. Why did he call it Phoenix? He's from the University of Arizona, and the University of Arizona is in Tucson. You made that too easy. No, it's in, the reason it's called the Phoenix has to do with the legend of the Phoenix. You know, the legend where the beautiful bird rises from the ashes of its own funeral pyre. And we did that sort of. Actually, I wanted to talk just a moment about the artwork. The logo for the Phoenix mission was drawn by one of the Canadian members of the science team. And you can see the phoenix bird and the beautiful plumage swirling together with water, and the tail actually points up to very close to our landing site up there. It's a very nice little bit of art. But we had our own funeral pyre. In 1999, we tried to land the Mars Polar Lander on Mars. How many remember Mars Polar Lander? Oh yeah, I worked on that as well. Mars Polar Lander. It failed on landing, just to give you the short story. It turned off the radio and then turned to enter the planet, and we never heard from it again. And so there was a lot of theories. Well, there were several theories as to what could have gone wrong. But bottom line is, we don't know because we never heard from it again. And at the time when we lost Mars Polar Lander, the next lander, a lander that was destined to launch in 2001, was already being assembled up at a clean room in Denver. And we said, the NASA looked at that and said, the analysis that has to go on to figure out what went wrong with Mars Polar Lander and any remedial actions, there's no way that we can confidently get all of that work done in time for a 2001 launch. And so they canceled the Mars 2001 mission. They wisely canceled the Mars 2001 mission. And so that lander was literally parked in a corner of the clean room, covered with a piece of plastic, and we went on. In the intervening years, we launched the Mars exploration rovers, which I'm sure you're familiar with, roaring success. Matter of fact, Spirit, the rover Spirit, just last week celebrated 2,000 sols on the surface of Mars. 2,000 Martian days of a mission that was supposed to last for 90. So the Mars exploration rovers are still going strong and are roaring success. But then in 2003, when the Scout proposal opportunity came, Peter Smith suggested that we take that lander that was parked in the clean room in Denver and refit it with a few new instruments and answer all of the concerns that we had about the Mars Polar Lander, all of the failure modes that we could come up with, and launch it as the Phoenix lander. And that's what we did. We analyzed the Mars Polar Lander's entry, descent, and landing phase and the design exceptionally carefully. It was given a great deal of scrutiny. There was several dozen issues, that each of which were insignificant probability that they could have occurred, but together, well, at least one of them did occur. And we went through every last one of them and answered them in the design phase and tried to take actions to mitigate the risk that those probabilities exposed us to. And so we launched the Phoenix lander. What did we take with us when we went to Mars? We took a bunch of imaging systems, and actually I'm going to talk to each of these as we go on through here. We took a robotic arm for digging and for doing some close-up examination of the soil. We took some chemistry experiments, and we took some weather experiments. Let me walk into each of these in a little more detail. We have a surface stereoscopic imager. This stands up on a mast. First of all, the optical elements here are separated just a little wider than a pair of human eyes, and they stand above the surface of Mars by just a little more than a human head. Basically, it gives you a human eye perspective, as if you were standing on Mars looking around when you bring the stereoscopic images back to Earth. The deployment mechanism for this one is one of my favorites. This whole mast is made out of fiberglass longerons, and you literally take it and you wind it down like a jack-in-the-box, and then they put a pin in the side of it to hold it in place, all during launch and cruise. And when we got to the surface, they literally pulled the pin and watched it go spring like this. It was marvelous to watch. In the deployment tests before launch, it would actually spin up and get to the top and go back down a little the other way and come back up. Scary as heck the first time you watch it, but it worked, and it worked like a charm. We also took the robotic arm camera. This is a camera that sat out on the wrist of the arm. You can see that it has a set of light-emitting diodes, red, green, and blue, both above and below the optics here. So this is actually when it's sitting upside down on the deck in the launch and cruise configuration. But what these light-emitting diodes allowed us to do is to actually dig a trench down where it would not have any sunlight to take an image, and then illuminate it in red, illuminate it in blue, illuminate it in green, and bring back a color image back to Earth. We took a descent imager. The descent imager is an interesting story in and of itself. It actually hung off the bottom of the lander on the side. The plan was that as we were hanging from our parachute coming down through the atmosphere, we'd take a picture that was 100 kilometers wide, and we'd take a picture that was 50 kilometers wide, and make a picture of 25 kilometers wide, and then right down and get pictures all the way down to the landing site. And just by looking at the pictures, you'd be able to say, we landed right there. Except that in the analysis that we did of the Mars Polar Lander, the interface between the descent imager and the computer was one of those low probability events that may have cost us the landing. That is, there was a very narrow timing window where if the interface card that the camera interfaced through caused an interrupt at just in this very narrow time window of the software, that it might keep the software from hearing from the inertial measurement unit, which is critical to landing. And we said, what's the probability that we're going to have this interface timing problem? Very, very low, darn near impossible. We tried to test it. We couldn't make it happen, actually make it happen in test. We saw it in the analysis. We saw that it was possible in the analysis, but we couldn't make it happen. And so we said, well, okay, we launched with the imager, saying we're going to take one image with the descent imager just to make sure that just to get that image during descent. And then during cruise, we continued the analysis, and we could not convince ourselves that the probability was 0 of this timing problem. And so the project made the very tough decision and decided to not use the camera. So we took a camera to Mars that we didn't actually use. And the hard part was that this was the flight spare from the Mars Polar Lander. So the outfit that made the camera down in San Diego made 2 cameras, sent them both to Mars, and got 0 pictures. We felt bad. Chemistry experiments. We took a thermal evolved gas analyzer, the TEGA. The TEGA is designed with 8 ovens, 4 on each side here. Each one has a pair of doors that pop open, and beneath that is a little screen and a funnel and down to a little oven, we call it. The oven is actually 3 millimeters across and 10 millimeters long. That's about the size of a Pentel pencil eraser. And what we would take a scoopful of Mars surface material and dump it into that little bitty funnel, and we would capture a little bit of the material in that oven. And then we would heat it up. And the instrument is a scanning calorimeter. The way a scanning calorimeter works is you add heat, you watch the temperature rise. You add heat, you watch the temperature rise. You add heat and the temperature stays constant, you know something's happening. If you're adding heat at 0 degrees C and the temperature is staying constant, that means you're melting ice. If you're adding heat at about 25, 30 degrees C, which incidentally is the boiling point of water in 8 torr of pressure, Mars pressure, then you know you're boiling off ice. If you're adding heat and watching the temperature stay constant at 359 degrees C, that means you're breaking down calcium carbonate. There's a whole bunch of thresholds where various chemical or physical reactions will take place. And by watching the temperature versus the heat that you add, you can tell something about the chemistry of the sample that you have in the oven. And then we were actually running a nitrogen purge through the sample at that time and running it actually through an evolved gas analyzer. You can see a little bit in the corner up there. It's actually a mass spectrometer, which would look at the gas that was being pushed off of the sample. We have the microscopy, electrochemistry, and conductivity analyzer. It's the MECA, we called it. The MECA is sort of the Swiss Army knife. It's actually about 4 experiments in one. We actually have 4 chemistry cells over here that you can see on the side. There's a better picture of them coming up later. You're seeing the top of the funnel here. What happens is we open a drawer underneath that funnel and then drop a sample of Mars surface material into that funnel. A little bit of it goes into the drawer comes in, and that sample is dumped into a beaker. And then we have a small reservoir of water. We took water with us to Mars, and we would melt the water and allow it to fall into the beaker and stir it up, and then we would add some reagent pellets in order to do a little bit of wet chemistry experiment in situ on Mars. The beaker was actually lined with some, what they call them? They call them ion-sensitive electrodes, ISEs, that would identify certain ions in the water just by the chemistry that I won't claim to understand. We also had an optical microscope. The optical microscope sits inside this box here, and actually I have an extracted view here. You can see the sample wheel with the edge of the sample wheel has a bunch of little bitty circular indentations in it. And that sample wheel, we would push that sample wheel out this way, which would take the rim of the sample wheel and it would expose it through a little slot right here. And then we would bring a sample of Mars surface material and dump it on top of that. And a little bit of it would get caught in the edge of the wheel. We then bring the wheel in, rotate it around 180 degrees until the sample that we wanted to look at was here, and then we could move that sample further in to get to the focal point of an optical microscope here, so that we could look at the sample grains at a microscopic level. And then on top of that, we could go a little beyond that focal point, and there was an atomic force microscope. We had an atomic force microscope. If that technology means anything to you, then I'm not going to try to explain how an atomic force microscope, but it allows us to look at the grain profiles at a nanometer scale. So between the SSI camera that was looking at the macroscopic level, the robotic arm camera that was looking at with like a hand lens, the optical microscope that's looking at a microscopic level, and the atomic force microscope looking down at a nanometer scale, we could look at Mars in a greater depth of scales than any mission that's ever flown to Mars before. The MECA also included the thermal electroconductivity probe. This is a probe that sits out on the wrist of the arm, and when you take the scoop and point it back, the TEC probes are actually pointed down, and you can drive those into the soil, and we could look at the degree to which the soil, the surface materials, actually conducted electricity, and therefore look for water content in the surface materials. It was also a temperature sensor. We could sense the temperature of the soil, or even sense the temperature of the air as well. The robotic arm. Robotic arm was our workhorse. The robotic arm was about 2.3 meters long, about 8 feet. And it had a scoop on the end of it that was as varied as we could make it. We had a blade with which we could scoop materials. We had a scraping blade here that we could actually take, and when we got down to a layer that was too deep in, we could go scrape, 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 and after we had some scrapings, then we could take the scoop and pick those scrapings up. And if it was too hard for the scraping blade, we had a rasp. This is basically a Dremel tool. The way the Dremel tool worked is on the bottom of the scoop, it stuck out like this, and then we would push the scoop down against the soil. It was spring-loaded, and you push it down against the surface, and that would drive the Dremel tool back up, and we spin the Dremel tool, and the spring would just push it back down into the material, the hard material. And the leavings, the scrapings from the Dremel tool would pile up in the back of the scoop here, and then by taking the scoop and lifting it around, we'd make them drop into this chamber and drop down in here, and then we could deliver that to the MECA or the TEGA, either one. We had a metrology package. We had a little weather station. The weather station consisted of a mast. That's the skinny one here in the middle. This has temperature sensors at various heights so that we could look at temperature profile. We'll see some data from that in a few minutes. We had a telltale up here at the top, which would swing back and forth in the wind and give us an idea of what what was happening with the wind on Mars. We also had a device called a LiDAR, which is like radar only with light. It had a laser beam that would point straight up into the clouds, and then a telescope that would look at the reflected energy. And by looking at the time delay that it took for signal to go up and down, and the strength of the reflected energy, we could get an idea of the cloud profile and the dust profile and the moisture profile in the atmosphere above. And we have some really good data on that from coming up here as well. So where did we go? We landed at 68 degrees north latitude, 233 degrees east longitude. If it was on Earth, it would be the northern coast of Canada. It is above the Arctic Circle. We landed safely. This is an image taken during landing by the Mars Reconnaissance Orbiter. It is, you can see actually, these two little specks here are expanded out here. You can see the lander hanging under the parachute as the parachute is deploying. If you have under the right projector, you can actually see the risers between the lander and the parachute. Actually, the crater that's behind there is the Heimdall crater. It's about 10 kilometers across, about 6 miles. And it's actually about 20 kilometers beyond the lander. We weren't landing in the crater. It's just the MRO was low and the angle was such that the crater in the background. A lot of people look at this and say, that's cool, you took a picture of one spacecraft with another spacecraft. It's more than cool, okay? This is actually one of my top 3 favorite images of the mission, and it wasn't even taken by my spacecraft. You got to realize that this is a picture of a bullet taken by another bullet. Okay, and the fact that they managed to do it with the Heimdall crater framed in the background is just phenomenal. This is a testament to the capabilities of the MRO spacecraft and the professionalism of the MRO team, and our hats are off to them. This is a magnificent image. MRO also took this picture for us. This is after we landed. You can see the enlargements of the 3 parts that we cared about. The lander, you can see this is the divot and the heat shield where the heat shield actually landed, and this is our parachute and the back shell. That's about the 300 meters from the lander to the divot, and about 600 meters from the lander down to the parachute. Of course, this one isn't quite as impressive. We weren't moving at the time. 8 days into the mission, we finally got around to looking underneath the lander. What happened was, before we wanted to dig in the Martian surface, we wanted to make sure that the lander was stable. One of the legs we could see from the SSI just by looking down. One of the legs, we took the arm and we took a picture of the legs hanging out, the leg on the other side. The 2 of them were easy to see. In order for us to see the 3rd leg, to make sure that the lander was sitting stable and not like up on a rock about to slip off or something like that, was to take the arm and to stick it underneath and take a picture underneath our belly. And that's the picture that you see up here. This picture was taken to make sure that this foot pad was sitting stable on the ground, and it is. And when this picture came up in the operations area at the University of Arizona, somebody in the back of the room looked at that and said, Holy cow. Because he realized what he was looking at. He realized that these bright spots that are visible in the surface material here correspond to the positions of the thrusters on the bottom of the lander. And what happened was, as the lander came down on the thrusters, as it was landing, the thrusters were throwing off the loose material that was sitting on top of this white hard stuff and revealing the solid ice that we had come to look for. Now, unfortunately, because of this strut here and all of the paraphernalia, we couldn't actually dig under and get to the material that we could see there. But we monitored that site repeatedly during the mission, and that was called the Holy Cow image. Actually, then this is another image, which is, I believe, looking down at the closer to the footpad that's over here. But this is another image of exposed material that was exposed by the thrusters as we landed. 20 sols into the mission, we had more evidence of water. This is a trench that was dug by the robotic arm on sol 20, and you can see that we came back and we did some other looking at horizon, looking at the sky, looking at other things for 4 days. We came back and looked at it again on sol 24, and you can see that the berm is unchanged. You can see that the trench, or the material in the trench, is all unchanged. The difference is that there's a white rock here, a white rock here, a white rock here. There's like 6 individual pieces of white material here, and in this image, they're gone. Which means either little green men came up and scavenged our rocks, or else they sublimated. Which means that what we had done was we had exposed chunks of ice in the bottom of the trench. We'd scraped them off of the hard surface underneath the loose materials, and we had these little chunks of ice sitting there on the surface in the trench, and during the next 4 days, they sublimated, evaporated straight from the solid to the gaseous phase. So more evidence that what we had found was water. TEGA was the instrument that was designed to look for water. And so you can see that we took a big scoop of surface material and we brought it over and we dumped it right on top of the screen that you can see here, and nothing went through. Because what we discovered, and this is a brand new discovery that the Phoenix made, is that Mars surface materials are sticky. The particles stick to each other in a way that we did not expect. And we had a screen, the opening to the oven is 3 millimeters across, and so the screen has openings in it that were 1 millimeter across, because they wanted to make sure that they didn't get chunks falling down into the funnel that would clog it and keep stuff from going into the oven. So they wanted to filter at 1 millimeter particle size, and nothing went through the 1 millimeter screen. And so we vibrated for days, and you can see how the material was sitting here, and then you can see how it has settled down. You're looking down at the top of the TEGA here, and you can see how the material has settled down on the screen, and eventually particles went through. We actually did manage to get particles into the TEGA. We actually did find water with the TEGA, but it took some trying. Yeah, sticky surface materials. That was one of the things we noted. And in order to get past that issue, that rather than dumping samples in large quantities, we developed a brand new technique which the system wasn't really designed to do. Well, it was designed to do it. We didn't realize that it was designed to do it. This was the imaginative operations team figuring out how to sprinkle small quantities of material with the robotic arm scoop, getting it to do that which we needed it to do that we didn't realize that we needed it to do before we launched. The robotic arm also had the capability, the robotic arm camera, actually we bring the scoop back up and we could put a little macro lens in front of the optics on the robotic arm camera and look at the actual clumpiness of the grains of Martian soil and how they cling together. What you're looking at here is this divot which is right across the front of the scoop right here. We also could take the robotic arm and look down inside the MECA wet chems, the funnels above the wet chem, to see that we were actually delivering sample there. The optical microscope, those circles that I showed you on the edge of the sample wheel, this is one of those circles under the optical microscope, and we could actually look at particles of a grain size. And then with the atomic force microscope, we could zoom in on one of these little micro machined little divots here. The divots are 5 microns in depth, The particle that you're looking there is 1/1,000,000th of a meter across, 1 micrometer across. And then where we could look at the profile, the shape of the particles on Mars, and we saw that they were rounder than we expected them to be. And here's a family portrait of our chemistry experiments after we made a mess of them. It's kind of funny. We showed this picture to some of the guys in Denver that had worked on assembly of the machine. Of course, they assemble spacecraft in a very clean environment. They don't touch anything with their hands, rubber gloves, masks, the whole bunny suit, the whole 9 yards. And then we show him, and he says, "You threw dirt all over our clean lander." The TECP also had some interesting data that was worth noting. We put the TECP in the soil, and what we could see is that the ability of the soil to conduct electricity took a spike during the nighttime hours, which tells us that water vapor from the air is transferring to the soil during the nighttime and then being liberated from the soil during the daytime, which is why the conductivity of the soil changes from day to night. This is showing us that there's more exchange of moisture between the soil and the air than we expected. Oh, the weather data. Weather data is great. This is the picture of that telltale that you saw on top of the mast. The interesting thing to note here is this square at the bottom is actually a mirror that's at a 45-degree angle, so that from the perspective of the SSI, we could take images of it and be looking up at the telltale. So instead of just watching it swing back and forth, we could actually see as it was swinging in circles and the pattern it was taking. The telltale turned out to be the most imaged part of the whole mission. We took more, because we would just sit there and take pictures of the telltale like this and then put them together in a movie like this to get an idea of what the wind was doing. We had calibration targets on the surface of the lander that we could which take a picture of a white disk, and based on how bright the white disk shows up in the camera tells you how much light is coming in at that time. We also use the colored disks to help calibrate the cameras repeatedly. This is some temperature data. I mentioned that we had on the temperature mast we had 3 different temperature sensors. One at 250 millimeters above the deck, one 500 millimeters, and one 1,000 millimeters above the deck. So what you can see here is that over sols 1, 2, 3, 4, 5, and 6, how the temperature goes up in the daytime, goes down at night, goes up in the daytime, goes down at night. That's the one interesting thing, and it shows you how warm it was getting, a balmy minus 30, and down to minus 80, C, bring a sweater. But the other interesting thing is to watch, and it's hard to see in this particular graph, but to watch during what parts of the day the top temperature sensor is warmer than the bottom temperature sensor, and what times of the day the bottom temperature sensor is warmer than the top temperature sensor, because what that tells you is during what parts of the day the surface is heating the atmosphere and what parts of the day the atmosphere is heating the surface. Direction of heat flow over the course of a diurnal cycle. And we had the temperature and pressure sensors going for 150 consecutive sols. We think we got 148 sols out of 150. There were a couple that we missed, but bottom line is we have a huge data set that goes across a whole season on Mars, and they're going to be analyzing that data for some time to come. This data here is from the LiDAR. This is the laser that shines up in the clouds and looks at the reflected energy. If you had a uniform distribution of dust through the atmosphere, you would expect the signal to become weaker from when it's reflected from a higher altitude. That's to be expected. And then we look at the deviations from that ideal curve to get an idea of at what altitude the dust particles are denser and therefore absorbing more of the laser energy. And so it is this deviation from this slope that shows us cloud density, particle density, moisture abundance in the atmosphere above the lander. We take that data and we integrate it over time. In this chart, where this is the light, the same. Well, this is actually from Sol 99. Though the other chart was Sol 70, but it is the same instrument data. And what you see here is over a period of an hour, from 4:23 to 5:21 in the morning, on Sol 99, you can see how the clouds are thickest between 3.5 and 4 kilometers above the surface. And you can see in that one spot straight above the lander how the density of clouds above the lander changes across that hour. And the other thing, and this is the one that really fascinated people, was that you could watch material falling out of the clouds above the lander. You're seeing snow. This is snow on Mars. Now, it was theorized that there was liable to be precipitation on Mars. We had never seen it before. This is evidence of, this is a discovery. Snow on Mars. This is also one of my favorite images.
Is that water snow or?
Yeah, it would definitely be water snow. The temperatures were far too warm for it to have been CO2. This is the mess we made of our work area. And you can see there's all the different trenches. You can see the piles where we dumped soils, rather the Mars. I keep using the word soil by accident. Soil is a funny word. Actually, I was reading one of Peter Smith's papers here recently, and he was using the word soil, so I feel a little bit better about it. So a lot of geologists are very picky. Soil has organics in it. We don't know that there are organics here, but some people call it soil. It's actually, the technical term is regolith, but that's too darn many syllables. The Martian, we dumped our tailings in various piles here, and actually there's science to be done there, looking at the angle of repose of the samples and how they slumped and how stable they were in the piles. This rock was actually sitting over here someplace. At one point we decided we were going to try to turn the rock over, and then they decided, well, we're just going to pull the rock and look underneath it at the way materials rested underneath a rock that had been sitting there for 1 million years. I was kind of hoping to find pill bugs, but we didn't find any pill bugs. I was a little disappointed, but that's okay. And this is a picture that was taken on Sol 151. Sol 151, we received data. We sent the command set up for Sol 152 and have not heard from the lander since. This is, you can see the frost that's forming on the surface and on the rocks, and it's darn cold up there. This was one of the last images we had of the rover. This is a rock called Quadling right here, which was one of the rocks that we were monitoring, just taking pictures of again and again and again during the course of the mission. This is one of our last views of Mars, which is also one of my favorite images. So what kind of science discoveries did we make? We found ice, both pore ice in the soil samples, as well as the segregated ice that was in a separate ice layer down below. We found, yes, the TEGA did find water. We found perchlorate, which we didn't expect to find. Perchlorate is a deliquescent. You know when you buy like electronics and there's that little envelope of white stuff that says "do not eat"? That's a deliquescent. It's something that sucks water, that absorbs water. And they put it in the electronics in order to keep the water from collecting on the electronics and causing damage. In Mars surface materials, the thought is that a deliquescent helps to control water transport between the atmosphere and the surface materials. And there's a lot of science going on in the data that we have with regard to the deliquescent factor of perchlorate. We found calcium carbonate. We found pH levels in the soil that were higher than we expected. I don't know if you heard the quote from one of the scientists that said that the soil is far better for growing asparagus than for strawberries, because it's, and the asparagus farmers loved that. We got points there. And we found precipitation from the clouds. Precipitation which had never been seen on Mars before. So that's some of the science that we did. So now let's talk about what it takes to operate a mission on the surface of Mars. Mission operations for a Mars mission have several factors that are unique to operating on a distant planet. Number one, Mars is far away. during our mission one-way light time, that is the time it took for a signal from the antenna on Earth to the antenna at Mars, was about 15 minutes. And of course, it would take 15 minutes for a signal to come back, which means you don't joystick this mission. You don't say, move the arm up and wait for the arm to move. And then move the arm right. No, move a little more right. No, no, no. You can't do a joystick mission at Mars just because of the one-way light time delay. And so what we had to do was build a system that we could send all the commands, all the instructions for a whole day, and let it go through its process, and then send its results back at the end of the day. Which means that all of the backhoe digging was done in situ by closed-loop control software on board the lander. All of the deliveries that we did, all of the wet chemistry experiments that we did, everything had to be done with day-long sequences. Let's see, another consideration is limited lifespan. When you fly to a place that you know the sun is going down in 90 sols or so, you have to make use of all of the time that you have at your disposal. We did pick a daily operations process rather than trying to do a one-week plan or try to do a half-a-day plan. We turned the planning cycle over on a daily basis, keeping in mind that a Mars day is not an Earth day. A day on Mars is about 40 minutes longer than a day on Earth, which means if the day on Mars starts at 8 a.m. on Earth, the next day it will start at 8:40, the next day it will start at 9:20, the next day it will start at 10 o'clock, the next day it will start at 10:40. If you wait 36 days, the beginning of your shift walks all the way around a 24-hour clock. We did that a couple of times. Let's see, we also had to take into consideration that we had limited resources. Our solar arrays would only put out so much power. We only had a limited number of ovens and chemistry cells. We only had a limited amount of data that we could send home on a given day, on a given daily basis. And we had a very limited ability to store data overnight. So most everything that we took, data that we acquired in a given day, we had to send home that night. And finally, we did not take a radio that could reach Earth. We were completely dependent upon the orbiters at Mars to act as relays for us. Now, the Mars exploration rovers had proven that relay operations work. As a matter of fact, of the data that's come back from the Mars exploration rovers, 90 to 95% of it has come back through relay. A small quantity has actually come back from the rover itself back to Earth. That's because the antenna, the transmitter that the rovers were able to carry to the surface of Mars is small and low power. It has an antenna that's about 30 centimeters across, and they have to use a low data rate. Whereas the interface between the lander and the orbiter is in the UHF band, and we can use a very high bandwidth. So the operational process that the Phoenix used is it waits until the orbiter flies overhead. Orbiter makes a pass. We get one pass from Odyssey or MRO about once every hour and a half, especially during the afternoon hours. The passes last anywhere from 5 to 16 minutes. And so when the orbiter comes up over the surface, over the horizon, you lock up that link in the UHF and you just throw all kinds of data as fast as you can up to the orbiter. And then when it goes away, it's okay, you wait for the next pass. And then the orbiter, because it's in space and it doesn't have to worry about carrying the radio to the surface, I'll talk about the mass implication in a minute, but the orbiter has an antenna that's about 2 meters, 2.5 across, and then a transmitter that has ample power to send that data back to Earth at a much higher bit rate. So you increase the amount of data you can get home, but you complicate operations by virtue of not being able to dock directly to the lander. The reason we didn't take a radio to the surface was a decision made very early in the development process. And this was a place where we weighed the benefit of taking a radio, taking an X-band radio to the surface versus the mass that it would cost us to carry it down. And we also had savings in complexity and testing in dollars, actually. There was dollar savings as well. But the main reason was because we didn't have the mass budget in order to take a radio with us. If we had taken a radio, we would have had to leave science instruments off. And we elected to maximize the value of the mission by taking more science instruments and not taking a radio. But it did complicate our mission operations some. So let's talk about a daily operations process that you have to go through in order to operate a mission on the surface of Mars. And a sol on Mars consists of the daytime hours and the nighttime hours, and the daytime hours and the nighttime hours. And the way our mission operations worked, sometime in the afternoon, the Mars lander would make contact with one of the orbiters and send back data. We usually would have 2 passes, sometimes we'd have as many as 5 orbiter passes, and each one would get a few hundred megabits of data coming back, and then at some point thereafter, the orbiter sends the data back to Earth, at which point our shift on Earth begins. There's a team of people that come in and look at the data and looking for 2 things primarily. How healthy is the lander? Are all the systems still working? And how close did the lander come to accomplishing that which we told it to do yesterday? And those 2 facts go into 2 planning processes: the strategic planning process, and the tactical planning process. The strategic planning process says basically, what are the science goals of the mission, and what subset of those science goals have we been expecting to accomplish this week, and what subset of those science goals did we tell it to do yesterday, and what should we tell it to do tomorrow? And so the strategic planning process looked at what we should do. And out of that strategic planning process, we would get the plan for tomorrow. We want to dig here, we want to take those images, we want to look at the sky at this time of day, we want to look at the sun at that time of day, and make it happen. And then the tactical planning process would take the plan for tomorrow and turn that into a set of commands. We would have instrument engineers, one for each of the instruments, who would write the command sequences to have his instrument do exactly what it was supposed to do. And then we would take those sequences and we would integrate them into a common master sequence, and we would make sure that that sequence lived within the power budget that we had, that would live within the communication scheme that we had, that would live within the boot time, the power up and the power down cycle time that we expected the lander to have on that day, make sure that the whole thing dovetailed together, and then we would send that up to the orbiter so that the orbiter could send it to the lander at the beginning of the next sol. So our planning cycle on Earth happened while the lander was asleep at night. And of course, we did this process every day, day after day. And actually, the strategic process, the planning cycle the tactical planning cycle, took inputs from the health of the spacecraft from yesterday, the daily plan from the strategic team, as well as the strategic goals that handed forward from the previous sol, as well as the communication opportunities both for uplink to the lander and for downlink from the lander, as well as the deadline that we had to get a sequence onto the orbiter. At the beginning, and then in addition to that, there was also the long-term planning process that worried about scheduling these communication passes, both to the orbiter from the lander and to the orbiter from Earth, for weeks out into the future. The tactical mission manager's job. That was the question I wanted to answer at the very beginning, remember? The tactical mission manager's job is focused on this arrow right here. My job was to make sure we had a command load go to the orbiter at the right time. Now, the best days as a tactical mission manager was the days when the daily plan that came out of the strategic process lived within the power margins that we had, worked well with the communication opportunities, that the health of the spacecraft was good and everything worked together, and the instrument sequence engineers put their sequences together and they dovetailed together without issue, and all I had to do was sign the form at the end of the day and stand there with my hands on my hips, looking at the horizon like the captain of a ship. And I actually had a few of those days. And the days when I earned my money were the days when we learned halfway through that there was a storm coming on Mars, and so the power budget was going to be decimated, or that there was a problem with something on the lander and we had to cut out science and we had to hack and slash and still have something to go to the orbiter on time that would do some meaningful science. Bottom line is the tactical mission manager's job. Oh, yes, keeping in mind that this whole process happens whenever it happens. The downlink may come in the middle of the night, and that's the beginning of our shift, and which regularly happens. Bottom line is the tactical mission manager's job is to work with the people doing the strategic planning, doing the tactical planning, to work with the people who, the data analysis, to make the team work as a whole. The real work was done by the people on the team. And a mission like this isn't run by a mission manager. The mission is run by the team. And I had a good team. I had one page where the fun facts that I thought I'd throw up here at the end, and just for completeness, temperature range we saw, it got down to a minus 143 Fahrenheit. That was on Sol 151. Got up to a balmy minus 3 Fahrenheit. Yeah. We saw wind speeds 2.2 to 27 miles an hour. But keep in mind that the wind on Mars is atmospheric pressure was like 1/100th of Earth's atmospheric pressure. So the wind is clipping along pretty good, but there's not a lot of surface pressure because there's just not a lot of molecules. Let's see, we had 90 sols of primary mission extended by 66 sols. And if you do your math real quick, 90 plus 66 is not 151. It's because on Sol 152, we came in and didn't get data, but we went ahead and planned Sol 153. And we didn't get data from 152, so 53, so we went ahead and planned 150. We went through the planning cycle 156 times, hoping against hope that we would get, that we had a momentary glitch, that something was wrong and that the lander would still be talking to us, and we didn't hear from it. We dug in 12 different places. Maximum depth was 18.3 centimeters. That's about that deep. 30,000 images, yep. 212, averaging 212 images sent home every day. 6 of 8 TEGA ovens used, all 4 of the MECA cells, and 7 out of 10 of those sets of divots on the edges of the optical microscope wheel. And we have plans for the future. As I said early on, we expect right now that the lander is encased in CO2 frost to a depth of about 30 centimeters. And that CO2 frost is going to persist likely until the first part of November, when the sun begins to rise above the horizon and beat the northern ice cap back some. Along about the 1st of November, we would expect the spacecraft to be no longer encased in CO2. By the first part of January, we're expecting the sun to be high enough that if the solar arrays are capable of putting out power, they will begin to do so. And if the solar arrays, because keep in mind that those solar arrays, you saw what the solar arrays looked like back here, right? Those solar arrays are like Japanese fans. They were all folded up against the side of the lander during cruise, and they open up like a big Japanese fan. They're not physically built to support 30 centimeters of CO2, of dry ice. So it's entirely possible that the solar arrays will be crumpled and folded and broken. It's entirely possible that the batteries will have cracked. It's entirely possible that the electronics have been exposed to minus 140 C temperatures during the course of the winter. The electronics may not boot. We're not expecting to hear from it. It's possible. We're hoping against hope. But if we do, okay, so what's going to happen in January is we will have one of the orbiters hail. As the orbiters fly over, it will turn on the radio and say, "I'm here." And if the lander is there, it will lock up, and the lander will say, "I'm ready to talk to you, but my watch is broken and I have no idea what time it is. What should I do?" And if the lander locks up and lets us know that it's there, 2 things will happen in very close succession. A whole bunch of jaws will drop open at JPL. And then we will very quickly scramble around and reassemble the team to actually make use of it. Because this test bed right here still sits in Tucson. The equipment is still in place to make use of the lander if it communicates with us in January. We are not expecting it. But if it does, we will make use of it. Because it would be very cool to just do nothing more than take pictures of that rock quadling and watch the CO2 frost recede. It would be very cool to turn on the temperature sensor and get more temperature data during a different season of the year, or to look back up at the sky and see whether the weather patterns in January, the weather patterns in the spring on Mars, are similar to the autumn that we were watching. You watch the news in January. If we hear from the lander, you can bet you will see that in the news. That's basically all I had to say. I will happily entertain any questions that you have this evening.
Yes, the first question I have is, where does the perchlorate come from? I mean, does it come from the water and chloride in the soil and UV light, or what? Where does that come from?
And now you learn the painful truth of the situation. There are two sides to an operation like this at JPL. There's the engineering side and the science side. I am squarely from the engineering side, and that's a marvelous science question that I have no idea the answer to. That's a good question. I don't know.
Because that's an ordinary pollutant on Earth.
No, on Earth, perchlorate is toxic to humans.
Sure.
Right? That's rocket fuel. That's the stuff that's out here in, right? But you know, there are microbes that are resilient, that will grow even in an environment where perchlorate is predominant. So it's toxic to humans, but not necessarily toxic to all life.
The other question I have is, are there any plans to photograph the spacecraft from an orbiter again? You know, to see if it really has
Yes.
ice on it, because it should be more reflective. And
Yes,
all that.
the MRO will be taking more pictures with the high-rise imager. But right now, it's dark, and the images wouldn't show anything. Once the sun comes up, because one of the things they will be looking for is to see whether those two solar rays, you saw those nice two little blue discs in that image. It would be very informative to know whether those two little blue discs are still nice round blue discs, or whether they're folded and crumpled and gone. Yes, sir?
Will that CO2 that form from the ground up, or will it precipitate from the atmosphere, or how will it?
How does CO2 frost form on Mars?
Yeah.
That's a darn good question. We saw on Sol 151, we could see it looking like a hoarfrost on the surface. But when it starts to build up, I don't know whether it precipitates out of the. We saw that snow precipitates from clouds. We were expecting that had we continued to watch, we would see more that water snow actually precipitating all the way to the surface. Whether CO2 frost forms in the same way or not, we don't know. I want to hear from the man immediately behind you, though. Yes, sir?
Why are you looking for life on Mars?
Because it's the next most interesting place to find life. We know that there's life on Earth. Well, we have pretty hard evidence that there's life on Earth. And we want to know whether, now that we know that there's water on Mars, we want to know that if water is enough to make life form. Because if it is, if simply the presence of water means that life generates itself, just by virtue of energy flow from a star and the presence of water, and life generates itself, then we could look out at other planets in the solar system and say, there's a pretty high likelihood that other places where we see there's likely to be water, there's also likely to be life. On the other hand, if we look at Mars and we see that there's this water cycle, and we know that there's an energy process passing through the environment, and we don't see life, then we say, maybe what happened on Earth is far more special, and maybe that there's a much lower likelihood that other planets in the galaxy have life. Make sense? Okay. Yes, sir?
What happened to all the water that you said were the canyon and the rock formations and stuff? What's the latest theory?
Excellent question. A great deal of it we think may be in the subsurface materials at the North Pole. And how it transports from that to a liquid phase in the mid-latitudes, there's a lot of conjecture on what that is. Another possibility is that over the millions and hundreds of millions of years that Mars is a fairly stable place. You know, Earth has a lot of tectonic plate movement, such that you can't find any surface material on Earth that's nearly as old as Mars. And a lot of the formations that we see have been there for hundreds and hundreds of millions of years. And so when was the Valles Marineris cut? And how much of the water that was present on Mars at the time is now trapped in the subsurface materials at the North Pole? And how much of that water evaporated to space and maybe collected someplace else, like Earth? We don't know. We don't know. There's a lot of conjecture and different theories. That's one of the interesting questions that would be marvelous to answer. It's another reason to go back to Mars again and again. Yes, sir?
Let's get it on the orbiter. First, how long do those orbiters actually stay in orbit? And then I guess also, how close does it actually need to be to the land unit to communicate?
The orbiters, proximity, I don't know. It's on order hundreds of kilometers above the surface. How close does it have? It has to be above the horizon. And so a pass that goes directly through the zenith above the lander gives us a communication window of about 16 minutes. If the pass is all lower on the horizon, we get 5 or fewer minutes. The duration that the orbiters last, Odyssey has been in orbit for close to a decade. MGS was in orbit before that, and Mars Global Surveyor. And that, they lost Mars Global Surveyor just shortly before we launched. The Mars Reconnaissance Orbiter went into service at Mars 2003, something like that. But they have a service life of, if they get a decade out of them, that's about right.
They don't fall out of orbit. They're high.
Oh no, they don't fall out of orbit, but they eventually will become.
Wear out.
Yes.
But they wouldn't decay, because, you know,
The orbits are not decaying, no. Yes, sir.
The Mars Polar Lander, did they ever find that by, I know there was a rumor that were kicked around one time that they saw in some spots some signs of a
The
rock.
high-rise does have images that show a lump. It looks to be like whatever landed appears to be covered in dust. A little thing, you know, a layer of dust that is constantly moving around and collecting on every surface on Mars. They do believe that they have imaged the site where we landed. Yeah. There was no significant information as to what caused the failure from that image. Yes, sir.
I have two questions. If you actually discovered further life, would you, one, approach it calmly, 2, take caution, or 3, run around screaming in circles?
You know, I would really look forward to having to make that decision. But keep in mind that if we find life on Mars, we're not expecting to find little green men with ray guns and antennas sticking out of their heads. We're liable to find life that is in the form of bacteria, or smaller, or something. Nothing says that life is going to be standing 6 feet tall and have 2 eyes and 2 arms. We would approach it with caution, I'm sure. Yes, sir.
Is any kind of research being done on Mars' moons? Or not moons?
Mars's moons.
Yeah.
Yes. I don't claim to know exactly what that is. I don't know that there's any missions planned to visit them. There was talk at one point that pointed out that landing on the moon of Mars would be easier than landing on Mars just because the gravity well is shallower. But I don't know that we have any missions in the works to go visit the moons of Mars. Yes, sir.
How much does this cost?
$428 million.
Is that a good, as space missions go, is that cost effective?
I
It's a tough question to answer, but I mean.
This was in response to a Mars Scout mission, which was a cost cap mission. That's how come I have a number for you. Was it a good investment? I think so. You're asking a value judgment there, and I won't claim to be an unbiased source.
That's about $1.40 a piece. So.
per U.S. citizen. I see. Okay. All right. Yes, ma'am.
How different was the surface at Phoenix and at, say, the rover?
Well, the surface at the 2 different rover sites was very different one from the other. In neither of those 2 sites did we have the hard ice layer just 5 to 7 centimeters below the surface. Both of the rovers actually. Remember, I was talking about how we discovered how to sprinkle with the scoop. Both of the rovers developed a trenching technique that they used with both rovers, where they could actually dig a trench with a rover that was never designed to dig a trench. They did so by taking the 6 wheels and turning them in so that they would rotate in place, And they would take 5 of the wheels and they would rotate this way, and they would take one wheel and spin it backwards like this. And then they would spin it backwards like this. And then they'd go back and forth about a dozen times, and they would have a marvelous trench digging tool that they didn't actually design it to do, but came up with after they were on the surface of Mars. And so both rovers had dug trenches that were on order 12, 15 centimeters deep, and neither one had any water in the subsurface materials. Meridiani Planum, where Opportunity landed, was a seabed, because they know that by the chemistry. That's where they found all the little hematite blueberries. And the other surface materials, and I'm not going to try to tell you the geology. You have to talk to a geologist to get all that. Gusev crater was a lot of basaltic rock, and it was a lot of basaltic being lava, being igneous rock. So it was a great deal more igneous in nature. So it was a very different set, a different location. Yes, sir.
Are there plans for a Phoenix 2 or Phoenix 1 left on?
No. Are we going to refly the Phoenix mission?
Yes.
No. Yes, sir.
Do you have any idea what your next mission to Mars is going to be?
Yes. The next one is the Mars Science Laboratory, which is the rover. Remember the Sojourner, Pathfinder, 1994, 96? It was a rover that was about the size of a microwave oven, right? Remember, Mars exploration rovers were rovers that were about the size of a kitchen table. The Mars Science Laboratory is about the size of an SUV. It is the deck of the lander stands about eye height, and the wheels are every bit as big as Sojourner was. Mars Science Laboratory is slated now to launch in 2011. It carries 11 instruments, which are going to be doing more searching for organic chemistry, organic molecules, life, than either Phoenix or the Mars exploration rovers were capable of. The Mars Science Laboratory is also powered by a thermonuclear, a nuclear source. It doesn't have solar arrays. It's got its own little RTG on the side, so it can drive at night and will last longer than the 90 days that the Mars exploration rovers were designed to. Yes, ma'am.
What is it like in the middle latitudes, and why are you exploring at the pole and not at those lower latitudes?
Both of the rovers are at the mid-latitudes.
Oh.
Both of Spirit and Opportunity are 12 to 15 degrees south latitude. So yes, they are exploring the mid-latitudes. This Phoenix lander was actually unique among the missions we have sent to Mars in that it was more than 20 degrees from the equator. Yes, ma'am.
That next project,
MSL.
how much is that going to weigh, and how will it get on the surface?
MSL landing scheme is, in my opinion, exotic. The MSL, the Phoenix, the MER rovers, right? They came in with a heat shield to slow them down. They used a parachute to slow down more. When they got close to the ground, they inflated this beach ball around them, right? And then cut the tether and bounced to a stop. Remember that, okay? The Phoenix lander took a different approach. We came in on a heat shield, and we deployed a parachute to slow us down, and when we got close to the ground, we jettisoned the parachute and fired thrusters to come down on jets, right? Okay? The MSL has a approach where they come in on a heat shield, they deploy a parachute, when they get close to the ground, they actually lower the lander from a sky crane, we call it. It's literally, and so the sky crane has got thrusters with the lander dangling beneath it, and it brings it down safely to the surface, and then cuts the tether, and the sky crane flies away and gets out of the way, so that the parachute and then all the other paraphernalia doesn't land on top of the lander. Which means that, and they've done the analysis that says it works. It says it will work. But they're lowering the lander through the plume of the sky crane as the thrusters are firing. And
The crane flies away?
oh well, it's thrustered. There's thrusters that are keeping it up, and they're slowing its descent. And as soon as it loses the mass of the rover, rover touches down, they lose that mass, then the thrusters are easily capable of taking the sky crane and lifting, giving it positive lift. It looks very interesting. I'm not working on the MSL mission. not by choice, but that's it. Yes?
Any advantage to that configuration?
Clearly, the designers of the mission have come up with this as the best solution to the problem.
One thing, you don't have to carry around all that rocket mechanism
Yes.
on your vehicle.
That's true.
Yeah. There are physical limitations to how big a beach ball you can make. Eventually, if the beach ball gets bigger, the thickness of the fabric gets larger, and then the mass of the whole structure becomes prohibitively large. And we couldn't come up with a mechanism. The MER rovers were about at the limit, the point of diminishing return, where making it bigger wasn't going to help. And so that's the mechanism that they have come up with, which is the best solution we have to the problem. Well, the man in the yellow shirt looks like he has another good question.
Does fire and smoke exist on Mars?
Excellent question. Fire and smoke, not like Earth. Okay? The difference is when we have a thruster, when we have a rocket thruster on a lander, we actually have to bring our own oxygen with us because there's no oxygen on Mars to speak of in the atmosphere that we can burn. When we burn something here, right, you have the fuel burning, and it's the oxygen in the air that's letting it burn. On Mars, the atmosphere is almost all carbon dioxide, and therefore, if you tried to light something, you wouldn't be able to. But the thrusters that we have their own oxygen inside with the fuel mixture, so that we have fire in our thrusters, but there's no fire on the surface of Mars. Okay? Excellent question.
How often have you had to improvise equipment for things that wasn't originally intended for, like on the lander?
Improvise equipment. I'm not sure I understand.
Really, I think it's like on the claw arm, or the wheels being used for something different than they were.
Trenching with more tools.
Trenching with designers are real good at coming up with solutions to the problems they know about. And when we get in situ, we occasionally meet problems we didn't expect. And when we can, we come up with solutions with the equipment we have at our disposal. How often does that happen? In my experience, when it needs to.
It sounds like it's almost every mission. You've had something you improvise.
You make do with what you got, right? You don't always go to Mars with the lander you want. You go with the Mars with the lander you want. Okay, I'm done. Thank you all. Thank you very much.
Thank you for coming.